Back with part 2, example 1. The expectations today and will be the next couple of days solving polynomial equations using various strategies, thus the many, many days, including factoring. So today we're going to concentrate on using the same technique that we had in the 3-minute review, which is factoring. And the idea of we've got one side equal to 0. We're going to make the rest of these in brackets, factors, and then we'll be able to pick off the solutions just as quickly as we picked off the x-intercepts of the polynomial function. So let's factor. Well, in this one, it's a simple trinomial, numbers that multiply to get 12, negative 12 rather, and add to get negative 4. What is it? It's negative 6 and 2, negative 6 and 2. So the numbers are negative 6 and positive 2. And then the solutions, again, two things multiplied, the answer is 0. And this is a step that we've done enough that you can skip this and get straight to the answer. I can see the answer here is going to be x equals 6, add 6 to both sides, or subtract 2 from both sides, x equals minus 2. So there are our solutions, those two right there. And this one, it looks kind of strange because there's no number on the end, but remember the first technique is a common factor first, right? Common factor first. So I'm going to pull out the r. What am I left with? R minus 8. And then this gives me r equals 0 or r minus 8 equals 0. Again, that's r equals 8. And there are my two solutions. Dandy. Factoring. Let's keep going. This starts to get more difficult, or at least it looks like it. It's got a cubic, so we might be thinking factor theorem from last chapter, but it is a common factor. There's no linear term on here, so I can pull out an x. I can't pull out 3x because 3 doesn't go into 17, so I'm going to pull out an x from there. And then I can see x equals 0 as one of my solutions, but from the second bracket, well, this is a hard trinomial, and I need to factor that somehow. You know, somehow I need to factor this, however I want to. Maybe I'll use the Aussie method this time, just for funsies. The Aussie method is, I know it's going to be two brackets like this. I put the extra 3 down under, like that, and it's still a number game, numbers that multiply to get negative 18. 3 times 6 is negative 18. Add to get 17. It's 18 and negative 1. 18 and negative 1. Those multiply. And then so there are my numbers. Plus 18 goes in there. And minus 1 goes in there. And I see the 3 actually divides into that factor, x plus 6. So my two factors are x plus 6 and 3x minus 1. And check that over real quick that I multiplied correctly. I can see the first term's correct and the last term's correct. The middle term comes from 6 times 3 is 18 and minus 1 is 17, so I factored that correctly. Notice I'm not done yet. I'm not done yet because I've got to solve the question. I've got 3 things multiplied equal to 0. I can see x equals 0 is one solution. X equals minus 6 is another solution. It's not as easy to see what value of x will make this bracket equal to 0. So sometimes I like writing these out. You'll get good at realizing what the answer is here. I add 1 to both sides, then divide by 3. I can see the x is 1 over 3. So then my solution set, and you'll see, when we end up having a whole bunch of solutions to a polynomial equation, we like to sort of gather them up in a set like this. And there's the set of solutions, the solution set and curly brackets. The next one, no common factor. Looks like it might factor by grouping, but it doesn't. And so what do we have to do? Well, if it won't factor, by common factor or by something special like grouping or difference of squares, something special, then difference of squares, then we're going to use the factor theorem. It's kind of a last resort for us, isn't it? Because it's so much work. So what I'm going to do is call that, I'm going to call that p at x, and then remember what I want to do is I want to find a value of x that if I substitute in, that I'm going to get 0. I want this answer to be 0 because then whatever I put in is going to be a factor. And I'm going to start small. Notice there's lots of things that divide into 12. I could try 1, 2, 3, 4, 6, and then 12, and then the negatives, -1, -2, -3. But I'm going to start small, and I think it'll work right away. I'm going to try 1. So I got 1 cubed minus 2 times 1 squared minus 11 times 1 plus 12. And lo and behold, it works right away. Okay, it's all good. So that's equal to 0. So we say, therefore, x minus 1 is a factor. And in fact, x equals 1 is going to be a solution to this polynomial equation. So now I'm going to use long division to find the other factors. X squared will do the trick here. Multiply the other terms, and then subtract down. Multiply x by negative x to get negative x squared, then positive x. Watch your signs when you subtract. And remember, the nice thing about the factor theorem is it's always got to work out, right? If this isn't 0, you goof something up, right? And so then, now I got, and this is a trick I'm going to pull, instead of writing this whole thing out, I'm going to say star becomes x minus 1 times x squared minus x minus 12 equals 0. Say, well, I can see that x equals 1 as a solution, but what about this garbage over here? Well, it needs to be factored still, right? And it factors into a simple trinomial, minus 4 and x plus 3. This has to be factored as well. And now I can see the solutions, right? X equals 1, x equals 4, x equals minus 3, and that's my solution set. So it is a bunch of work, but that's not so bad. And it gives us another reason to do that super fun skill of long dividing polynomials. All right, good luck on the homework. It's both in our little thin textbook and in the hardcover Addison Wesley textbook. So have fun with that. Thanks for stopping by.